Hey yo yo, we be doing chemistry with Mr. Lum again. Anyways, we're going to be doing talking about acid and base titrations. My B block class wanted me to say that, so I did it for them. Anyways, so let's get into it and talk about acid-base titrations. Titration is done so that none of the reactants are in excess, and that is the point of titrating something. You reach a stoichiometric equivalence point, and that means nothing is in excess. So let's do a question right here. If nothing is in excess, 25 milliliters of 0.200 molar HCl is titrated with 0.112 moles per liter of calcium hydroxide. How much calcium hydroxide was used? Okay, so what we want to figure out is we're given milliliters and molarity of HCl, and we're given molarity of this. What we want to find is milliliters of this. So the first step in solving something like this is first write a formula. Okay, so we're going to write HCl plus calcium hydroxide and that's going to make CaCl2 and H2O. Okay. Now the first thing that we should notice is that this is not balanced. Okay, this is not a balanced reaction. We have 2 chlorines here and only 1 chlorine on this side. So the first thing I should do is try to balance it. I'm going to write a 2 right here. Okay, so the next thing I notice is I have 2 hydrogens and plus another 2 hydrogens. I have 4 hydrogens here and only 2 hydrogens here. So I'm going to put another 2 right there. 2 hydrogens, 4 hydrogens on the reactant side, 4 hydrogens on the product side. Calcium is balanced, chlorine is balanced, and oxygen, there's 2 and there's 2. So everything, this is now a balanced reaction. Okay. What we can figure out now is we can finally figure out how many milliliters of calcium hydroxide we use. Okay, so please remember that molarity equals moles over liters. Okay, so what we want to find is we want to find liters. So we're going to go liters equals moles over molarity. Okay, now let's make this thing happen right here. Let's find out how many moles of CaOH we need, and then we're going to divide by the concentration of CaOH2 to find out how many liters we have. Okay, so I'm going to take HCl, and that's going to be 0.2 moles per liter of HCl. Okay, and well, I guess we can write this too, HCl. Now what I'm going to do is I'm going to change this into moles of HCl by multiplying this by 25 milliliters, or in other words 0.02500 liters. Okay, and then I'm going to multiply this by, well, what we see here, there are 2 HCl being used for only every 1 calcium hydroxide. So I'm going to go 1 calcium hydroxide, CaOH2, is equal to 2 HCl. Okay, so I'm just going to cancel a few units so we can see a few things. So moles per liter times liters, well, our liters is going to cancel. Okay, and HCl is pretty much a unit too. And if 2 HCl is equal to 1 calcium hydroxide, well, we have these canceling. And now what we have is we have moles of calcium hydroxide. Okay, so we figured out this part right here. Now, if we divide this by the molarity, we'll figure out how many liters we have. So I'm going to divide this by the molarity, which is 0.112 moles per liter. Okay, and what happens is this cancels out with this, and we're left with liters. Now I've done this calculation already, and I found that it equals 0.0223. Okay, 3 sig figs, 4 sig figs, exact number, 3 sig figs, so it's 3 sig figs, or in other words, I can just say something like this: 22.3 milliliters. Okay. Okay, so this is some basic stoichiometry that we just did right here, and now we're going to look at some different stuff, some different acid-base kind of titrations. Okay, here is our next question, and well, first we have a little bit of a vocabulary to do. The vocab that we're going to be doing is partial neutralization. Partial neutralization means when you have a polyprotic acid, and a polyprotic acid has many protons that can be neutralized. Each proton that is neutralized is called a partial neutralization. So let's take a quick example here, like H3PO4. Okay, if one of these is neutralized, this has 3 protons, it's a triprotic acid or a polyprotic acid. If one of these hydrogens is neutralized, it'll become H2PO4 minus, and then another one can be neutralized, and it will become HPO4 2 minus, and then it can become PO4 3 minus. So this can have up to 3 protons that are neutralized, or 3 hydrogens that are neutralized. Now, each time one is neutralized, it's called a partial neutralization. Okay, so this is the one partial neutralization, and here's another one, and so on and so forth. Okay, so that is what a partial neutralization. It's when a polyprotic acid, each proton is neutralized, and that each one is defined as a partial neutralization. Now, here's a question right here. It says 1 mole of H4P2O7 is titrated with 3 moles of KOH. So again, we're using that word titrated, which means nothing is in excess. Okay, so if you have 1 H4P2O7 and it's titrated with 3 KOHs, okay, what's it going to make? Well, it's going to be making KHP2O7. Now there's 3 OHs. Okay, so we can kind of ignore this K a little bit, and there's 3 OHs, and each OH takes 1 hydrogen away. So there's 3 of these, so it takes 3 hydrogens away, and that means we're only left with 1. Now there's 3 Ks, so that should be 3 Ks right there. Okay, so there's 3 OHs, and they combine with 3 of the hydrogens here to make 3 waters. Okay, and that's a partial neutralization. Okay, it took off 3 of them. Okay, that's a pretty straightforward, easy problem. Let's move on to a little bit more difficult one. It says right here, an equivalence point is reached with 25 milliliters of NaOH and reacting with 58.10 milliliters of 0.02700 moles per liter of H4P2O7. Write a balanced equation. Okay, so the first thing that we should do is figure out how many moles of OH are we using, or how many moles of NaOH are we using, and how many moles of H4P2O7 we're using. So let's get into it. First, moles of NaOH. Okay, this is going to equal, well, we have moles per liter right here, so it's going to be 0.1255 moles per liter, or in other words, molarity, and we're going to multiply that by the amount of liters we have, which is 0.02500 liters. And I've done this calculation as usual, and I found that this is 3.1375 times 10 to the minus 3 moles. Okay, now we're going to calculate the amount of moles of acid we used. So moles of acid, or in other words H4P2O7, and that's going to equal to 0.02700 moles per liter times by our amount of liters, which is 0.05810 liters. And we see that this equals made a small mistake, 1.5687 times 10 to the minus 3 moles. Okay, so 1.56. I should write that again and be a little bit better. 1.5687 times 10 to the minus 3 moles. Okay, just ignore that ugly writing. Okay, so now that we have done this, we need to find a ratio between the two. So I'm going to find a ratio by going moles of base, NaOH, divided by the moles of acid, H4P2O7. Okay, and that is going to be equal to 3.1375 times 10 to the minus 3 and 1.5687 times 10 to the minus 3 moles. And we find that this equals 2.00 of NaOH and over 1 H4P2O7. So what does this ratio mean? Well, it means there are 2 moles of NaOH used for every 1 mole of H4P2O7 used. So in other words, it's 2 to 1. So we can make our formula that looks like this. H4P2O7, there's only 1 right here, 1, Okay, and that is going to be plus 2 NaOH, because there's twice as much NaOH as there is for H4P2O7, and that is going to make Na2. It uses 2 OHs, and so it takes 2 H's from here, so it's going to be 4 minus 2 is 2. That's how we get the 2 here. P2O7, and we get 2 waters. Okay, and that's it.